We've established that the processes embedded in MCS evolution that are the primary target of TropSat evolve on short timescales and fine spatial scales. They are also characterized by variability in a range of physical parameters. In this section, we'll identify those data types. We'll document how that data is currently collected, and we'll cover how those current sources and methods are not yet sufficient to allow understanding of MCS dynamics and upscale connections. We'll start with a quick reference list of the MCS data types that TropSat will measure. The system will generate swaths of multi-layer observations in temperature and moisture. Those swaths will include simultaneously extracted measurements of sea surface temperature, outgoing long-wave radiation, rainfall rate at the surface, and surface vector wind field. When we say vector here, we mean the wind data recovered as both wind speed and direction. Both are necessary for calculating the divergence and vorticity fields that serve as indicators of convection and subsidence within an MCS. So let's take a look at how this array of data types is collected currently. First, we'll look at column and layer measurements in moisture and potentially temperature. Those will primarily provide insight on both MCS precursor and successor states. Readings at multiple levels will allow close observation of changes in the planetary boundary layer at MCS breakout phase. We expect to see measurements that characterize the upward perturbation of that layer as initial moisture plumes push through and aggregate upward to larger scale. We'll derive valuable information on stratification in the atmosphere as well, and the effects of differing levels of stability on convection growth. And we'll see these effects in both the upscaling and the decay phases of MCS development. NASA's Moderate Resolution Imaging Spectroradiometer is a current generation instrument for detecting atmospheric water vapor. It's being flown on multiple polar orbiters. With those multiple sources, MODIS produces nice worldwide daily summaries of total precipitable water, but they are of limited value for MCS study. They lack required resolution in both time and space. Once-a-day sampling isn't useful for characterizing a process that's evolving on an hourly basis. Moreover, even with multiple sensors, there are significant gaps in MODIS output. The black areas in these plots represent missing data, due either to holes in the overflight coverage or to interference by deep cloud cover. If we zoom up on the South China Sea study area we've used as our example, we can see this. Because much of the area on these days is involved in a deep tropical disturbance, there is almost no useful water vapor data. And with that once-a-day output, even the event precursor and decay stages are missed. We'll contrast how TropSat will sample in all these data types in the next video. For the moment, we'll move on to how sea surface temperature is currently accessed. As we've discussed, convection is powered by heat from below. That makes sea surface temperature an important driver for convection at the mesoscale. The warmer the underlying ocean surface, the more energy there is available to power MCS growth. Sea surface temperature is observed by radiometers. Those are passive instruments. They cannot see through clouds. So while key to understanding MCS growth and decay, SST data is not available during MCS mature phase. As a result, SST measurements will be primarily used to characterize precursor and successor thermodynamics in the MCS life cycle. Looking at what is currently best available SST data will provide a useful snapshot of TropSat's value from a sampling frequency perspective. These plots are from NASA's second-generation Advanced Microwave Scanning Radiometer. The instrument is on a polar orbiter, so it has the same repeat issues we've been referencing. It covers the same area of the globe twice a day, but coverage leaves gaps. We'll use this larger study area from the Indian Ocean through the Western Pacific to illustrate. These are the morning passes for the 2 days in December 2014 over which our South China Sea example occurs. The patchy appearance in these swaths is data dropout due to cloud cover. Here are the afternoon passes for those same 2 days. The red boxes show the South China Sea event location. We'll zoom up on that area in a bit. The coverage precesses to the west, so gaps are filled on the following day, but that means the time interval between samples for a particular area can be up to 48 hours. That becomes more clear when we plot both morning and afternoon passes for both days. As we do that, for clarity, we'll add the adjacent swaths themselves, first the morning passes, then the afternoon. The coverage issue becomes immediately clear. We can zoom in to highlight that further. For our fast-evolving South China Sea event, there is no SST coverage at all during the precursor stages that occur late on the 27th. On the 28th, there are 2 passes that occur during mature phase, but by that time there's so much cloud cover that almost no relevant SST data is available. TropSat does not solve the cloud issue. It will not gather SST data underneath a mature MCS. It will, however, capture multiple samples during both the precursor and succession stages of MCS evolution. Moving on, we have outgoing long-wave radiation, or OLR. The animation you're seeing is OLR data for the 24-hour period leading up to our South China Sea event. OLR measures energy leaving the top of the atmosphere in watts per square meter. Where convective activity is strongest, clouds push to the top of the troposphere and even slightly beyond. Those cloud tops are coldest, showing deepest blue in the imagery. In areas with no clouds, OLR is driven by much warmer sea surface temperature, indicated by oranges and reds. OLR data is synthesized from multiple sources and generated every 3 hours. It's relatively low in spatial resolution. Each OLR sample represents 1 degree of latitude, or about 111 kilometers on a side. The pixelated animation output shows that sample size. OLR is a good indicator of large-scale dynamics, such as active phases in the Madden-Julian oscillation. It does indicate areas of strong MCS activity, but it does not resolve MCS details. Next, we'll look at surface rainfall rate. For that, we turn to another synthesized dataset, this one from NASA's Global Precipitation Measurement Mission, or GPM. The animation covers the same 24-hour period leading up to our South China Sea event. GPM data is higher resolution in both space and time. It's updated every 30 minutes and comes at a 0.1 degree pixel size, or about 11 kilometers. This level of resolution is the result of combining data from instruments flying on 9 different international satellites. Higher resolution allows us to zoom in and explore detail. Measurements are in millimeters per hour. Red zones show the location of high rainfall rates. In active MCS events and larger scale tropical disturbances, those areas are likely to be associated with strong convection. Blue areas indicate the lower rainfall rates associated with stratiform precipitation. Here, a clarification on synthesized data as it pertains to MCS analysis is in order. Both GPM rainfall rate and OLR data are reconstructed or modeled from data gathered by multiple sources. As part of that process, the data is resampled to a regular grid. This makes for convenient coordinate systems for mapping purposes, but the modeling process is basically a sophisticated form of interpolation. It inevitably averages out important information in some places and makes educated guesses in others. Given the high spatial and temporal frequency at which MCS evolve, these synthesized datasets are not adequate for capturing the physical processes at work. Accomplishing that goal will require sampling all data types at the highest possible resolution, at the same time, and at the same location. For features at the mesoscale and upwards in size, that dictates spaceborne sensing systems. A physical parameter required for detailed study of mesoscale convective systems that is gathered in this manner is wind. Large-scale wind fields are retrieved by spaceborne scatterometers. The data is in swaths. Where precise wind field observations are available, important indicators of convection can be derived. The swath shown here is from the RapidScat instrument on board the International Space Station. RapidScat was a high-resolution sensor generating data samples at 12.5 kilometers on a side. Zooming in on our South China Sea area, we first show the wind field itself. That's plotted over the GPM rainfall rate data that is closest in time to the scatterometer's overflight. From the surface wind field, we can derive convergence and divergence. Where convection is occurring, air rising from the surface needs to be replaced. In those locations, there will be net surface inflow. That will show up as convergence in the wind field. Convergence is mapped as blue in the scatterometer swath. Deepest blues indicate areas of strongest convergence and hence strongest convection. Where subsidence is occurring, the descending air needs to move outward when it encounters the surface. In those areas, there's outflow or divergence. Divergence is mapped to red in the swath data. Red indicates areas of subsidence. The fundamental challenge we face in study of mesoscale convective systems using current data sources is sampling frequency. MCS cover large areas, so spaceborne observation is a must. The relevant instruments exist, but they're deployed on platforms in high inclination orbits that don't revisit target areas with adequate frequency for resolving rapidly changing conditions. To demonstrate, we'll again use our South China Sea example, but this time overlay all the available scatterometer passes for the period. There were two systems flying at the time of this event. Those were ASCAT and RapidScat. ASCAT produces two narrow swaths. RSCAT passes are the wider single swaths. If we composite the passes from both sensors into the same 24-hour animation of surface rainfall data we've used previously, we see a good illustration of the sampling dilemma. Due to their high-angle orbits, they pass over areas of specific interest in the tropics very infrequently. To emphasize this point, we highlight the areas of our South China Sea event briefly when each of the scatterometers passes over. We've demonstrated that the system develops in just 12 hours with rapid upscaling of convection into a full tropical disturbance. During that time, there's a single pass by each of the two instruments. It's certainly a useful snapshot because the two passes occur just 30 minutes apart, allowing comparison of data from the two sensing systems. But it does little to capture the life cycle of the convective processes at work. There are two additional points to note here. The first is that during the larger multi-day MJO event in which this storm was embedded, this is the only instance where near simultaneous MCS coverage by the two instruments occurs. Secondly, the reason these studies have been conducted using data from late 2014 is that RapidScat lost calibration in mid-2015 and then failed altogether, leaving only ASCAT currently as a source for high-resolution ocean vector wind from space. Thanks for viewing this video on sources of data that are currently available for study of mesoscale convective systems. In the next segment, we'll cover how TropSat will expand coverage of MCS relevant data spatially, in time, and by type.